angel and a devil on his shoulders, and then the devil just takes over like half the time.
Reactant to product, you got that. That's what we're going to call the forward direction. If this has a double-sided arrow, now that's an equilibrium. What that actually ends up meaning is if you have a beaker, let's say with some water in it, if that beaker is closed and sealed, so there's an actual lid. Why did I draw a line? A lid on the top. Now this can reach equilibrium. So what's going to happen is the water will escape, and the water particles that are up here are going to return into solution. At some point, the rate of going up is equivalent to the rate going down. How do you know this water bottle will have that to be true? That the rates up and the rates down have to be equivalent. What visual observation tells you that? Yeah. It means that the quantity of water, liquid, phase state, is not changing. And then if you evaporate 2, you put in 2. If you evaporate 3, you put in 3, right? So this is the rate forward, rate reverse thing. Concentrations are not equivalent. They stay the same.
What do you mean? Like?
Yeah, I'll show you. Okay. Let's try to show that here. At the beginning, let's say the moment you pour water in, the moment, and you seal it very fast, your rate of reverse, so let's put a phase state sleeve. This is H2O liquid, this is H2O gas, so this is your forward rate of reaction, this is your reverse rate of reaction. The equilibrium expression has, you don't need to know this, but it's written as K. K is an equilibrium constant. It tells you about how fast things are going, just in general. You're not going to do any calculations with it. It's the concentration of the reactants or the products, but these have to be aqueous phase states or gases. Okay, solids and liquids don't matter, but you're not going to calculate with that. Here's what we have. At the very beginning, when you dump water into that beaker, do you have any water going back down into the liquid phase state? So do you have gaseous water vapor the moment you dump water in? Don't overthink that. No. So the rate of the forward reaction and reverse reactions eventually will look something like this. So I'll show you, and then we can talk about which one is which. Okay. One of these lines represents the concentration of the reactant, and the other line represents the concentration of the product. Which is which? So which one of these is reactant, which one of these is product?
Product is bottom, reactant is top.
Okay. Why do you say that? You're right.
Because you can't have product immediately. You have to have,
Perfect.
Has to have time.
Yeah. At time equals 0, you have all liquid phase state, and that liquid begins to decrease and into gaseous. The gaseous phase state begins to increase until their concentrations remain constant and unchanging. When you hit this region here, where the concentrations are remaining constant, you've reached equilibrium. So the rate forward equals the rate reverse. So let's call that a rate now. The rate of the reactants going to products, so I'll call that rate forward and rate reverse.
Okay, wait. Okay.
Yeah.
So originally, when I asked you a question about if like the energy values for chemical reaction occurred was 0, like it didn't lose or take any energy, you said that it just shouldn't happen. Is this what's happening here?
Keep going. What do you mean? Keep going. Refresh my mind. Keep talking.
Okay.
Yeah.
So I think it was during like I don't know what unit this was.
Yeah.
I just remember asking you a question of, let's say the amount of energy required versus the amount of energy so the amount of energy required and the amount of energy released when a chemical reaction happens. What if it's 0? Like should the is that a thing? And you said
Did they cancel each other out?
yeah.
Is that your thing? That's okay.
So is that what's happening here?
No.
Okay.
Yeah. No, but two parts of that. That's okay. Is it likely? No.
Okay.
That they perfectly cancel each other out, and the amount of energy you put in with the amount of energy you get out, very unlikely. This, not dealing with energy, just actual amounts, concentrations, values of the quantity of material in the solution.
So, okay.
Nothing about energy here.
So why, okay.
Yeah.
So how is it a reverse reaction? How can it be a forward reaction and reverse reaction?
Yep. Let's, not everything, I should say it carefully, not everything has an equilibrium necessarily. And by necessarily, I mean there's a whole bunch more to equilibrium. Let's keep this simple. Let's try to answer that this way. If I put a hole in this, what will that do to this reaction? Will it force more water, liquid, to turn into a gas? Or will it force more gas to turn into a liquid if I put a hole there?
Liquid to gas.
Why is that?
Because it won't go back.
Keep going.
It's evaporating out of the air.
There you go. These gaseous particles are escaping, and when you do so, doesn't that mean more liquid water can fill that void, right? So it increases the rate this way. If you increase the rate forward, what happens to the concentration of the reactants the moment, or products, it doesn't matter, the moment you put a hole in there?
They start to decrease.
So, should I see a spike like this? Something like this?
No, because they'd continue to escape until it was all gone.
Yeah, and then
So,
let's say we seal it now.
Oh. Well then, yeah.
Yeah.
Yeah, something like that, where a new equilibrium is achieved at a higher concentration than what it was previously, right? But this is called Le Chatelier's principle.
I think we all need to learn how to spell this word so that you can.
We're gonna see it on like
You
an
spell it
ACS
differently
exam.
every
I'm probably
single
gonna do
time.
it. And if
Let's
we're like,
chat
what is
to
this
the-
principle? We never learned it.
You don't remember it's one.
Here's what I found.
Yeah, what is it?
Sorry.
No, what is it?
You're missing an E before the L,
E before the L,
but otherwise you're right.
this one, nice.
Oh, wow.
Wow.
Good job. Dang.
Oh, culture.
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 Yeah. The
Oh.
Le Chatelier's principle is the one thing you want to take away. Le Chatelier says when something has reached equilibrium, and they call this actually dynamic equilibrium, not a big deal. It just means that we're talking about two phase states. Okay, equilibrium. When we reach equilibrium, if we do something to change equilibrium, put a hole in there. If we shake the container, we change equilibrium. If we push on the container, we change equilibrium. If we add water, we change equilibrium. If we
So
heat it
any
up,
of the factors
right?
change and you're.
if you heat it up, you change how much gas is going to be produced. If you do something to the system that's initially at equilibrium, Le Chatelier says it will reestablish equilibrium again, given enough time for that process to occur. That's Le Chatelier. Which way will it favor? That's a little bit of a different question, but we just answered that, right? If you put a hole there, it favors going towards the products, right? What if we heat this up? So no hole, but we heat it up. Which way will be favored? And by favored, I mean what's going to happen initially? You're going to form more gas, so the concentration of the products is going to increase. The reactants initially begin to increase a lot too, because you have a whole bunch of gaseous phase state here that you can dump back into there, reestablish equilibrium. What if you cool this down to remove the heat? What will happen?
Both begin to drop.
Yep, the products begin to drop, reestablishing equilibrium. The reactants, because there's not enough gaseous phase state, begin to drop, reestablishing equilibrium, so on and so forth.
Okay.
So every time you pick up your water bottle, Le Chatelier is occurring. Yeah, I mean, that's it. I mean, not to over-exaggerate. What about this graph? Is this a possibility? Can you do, let's say, concentrations and have a situation like this?
Whoa.
Is that a possibility?
Probably.
For, why did I call those rates in my brain? Concentrations, we're doing concentrations. Sorry, reactant and product. So reactant, product. Is that a possibility? What does that mean?
Decomposition. We were breaking the.
It just means you form more product than reactant at equilibrium. We have more reactant than product at equilibrium. If you're an industrial process, which one do you like better? This one or this one? You're trying to sell a product to the consumer. the bottom, right? You want way more product than you want reactant consumed. And then is this a possibility to do something like, is that a possibility? Reactant and product?
Yeah.
Yeah? Is it likely? No. That you have exact same concentrations. And then the last one is, and this is where I was trying to do the rate, if you measure those rates, the rate forward, the rate reverse is coming together. So this is true. This is the forward rate of the reaction, this is the reverse rate. And then at equilibrium, those rates are equivalent, right? Rate forward equals the rate reverse. Yep. That's equilibrium.
The concentration,
Yeah.
do they have to move the equal amount of distance? Like, so
Like
could,
this guy?
yeah, so like could the reactants only go down like a tiny bit and then the products come up with a lot more to equal out? Or,
Yeah, let me think about that. So you're saying something like this, and then
like,
go down?
can I draw it?
Yeah.
You're sorry, go.
If you had one, and so like the products
Yeah.
went like this, and then the reactants only came like that.
Yes.
Okay.
Yes, yes, absolutely. Yeah, so, so what Gloria's getting at is this is, when I use the word rate, we're not gonna talk about this at all, but it's actually called kinetics. And the speed at which something occurs, so the product going very quickly, the reactant not going so quickly, because of the actual, intermolecular forces, energy associated with that, three-dimensional geometry, how often do they collide, so on and so forth. So that's absolutely possible, yeah. Okay, equilibrium.